Okay, so now this is the second problem. It is more or less same, so maybe we'll spend less time with this question. So here you see the air flows over a flat plate and the velocity is 40 meter per second, 25 degrees centigrade at temperature around 1 atmosphere pressure. What is the flat line should be used to achieve the Reynolds number 1 and 10 to the power 8 at the end of the flight? So that's the first question. And if the critical Reynolds number is this, at what distance from the leading edge the plate would transition occur? So if you can remember, during the lecture we already discussed this. So the flow will be laminar and turbulent. We already know that. Okay, when the flow state becoming turbulent, we say this is this distance, it is called the critical distance. And at that point when the flow will become turbulent, we say the Reynolds number, it will be C5 into 10 to the power 5. So this is actually the formula we know from the theories, that the flow will be turbulent at this point when the critical Reynolds number is 5 into 10 to the power 5. So when we are solving this question, you will see here the first question is we need to actually calculate the length, where it will be the Reynolds number will be 1 into 10 to the power 8, which is definitely the turbulent flow. And the second part is we need to calculate the distance from the leading edge, where the Reynolds number will be 5 into 10 to the power 5. That means when the turbulent will start. So as it is, we said it is the isothermal conditions exist between the flat plate and the fluid flow, and the properties are constant. We got the kinematic viscosity because we know, we already discussed when we solved the first problem. So let's say this is the flat plate again. We have the pre-stream velocity is going this way. Okay, so this is the pre-stream velocity. This velocity is given 40 meter per second. So this is 40 meter per second. So for the first part, we will calculate, you see, what plate length. That means we will calculate the length. We know the definition of the Reynolds number. So this is actually the general definition of the Reynolds number we used for the last problem. It is the pre-stream velocity, characteristics, length, and kinematic viscosity. Don't be confused. When I showed you the slide, maybe you saw dynamic viscosity, density. Actually, we all know the relations between kinematic viscosity, dynamic viscosity, and density. So here we are using the dynamic kinematic viscosity. Anyway, so the Reynolds number here is 1 into 10 to the power 8. It is given, and the velocity, it is given 40. We need to calculate the LC. We already know the kinematic viscosity, so we can write LC equal gamma. This is this is new, the kinematic viscosity, Reynolds number, and the velocity v. So if we substitute all values, then we'll get this line. This is just, we solve another problem, and this is very simple, so I'm not spending much time with this. So the second part of this question is, at what distance from the leading edge the transition will occur? The critical Reynolds number given 5 and 10 to the power 5. So if this is the length, if this is the total plate, let's say at this distance the flow will become turbulent. So let's say this is the laminar section and this is the turbulent section. The flow will become turbulent at this section. So this is the stage when the transition will start. So actually transitional state occurs just earlier. After laminar we have the transition and then the turbulent flow. Anyways, so we'll calculate the distance. So the distance from the leading is for the transition to take place with a critical Reynolds number 5 and 10 to the power 5. We can write the formula, if see the xcr, it is equal the new kinematic viscosity, and the Reynolds number cr means the critical Reynolds number, and the velocity. You can ask me, um it was L. Okay, you can use it is. So when it is the critical Reynolds number, I should, from the formula, we usually define this distance as x. This is for flat plate. Maybe when it is a cylinder, okay, maybe when it is a sphere, then instead of the characteristic length, in some cases you need to use the diameter. So that we will explain later on when we will solve this sort of problem. Maybe your tutor can solve some problems. In some cases you may get a Coke can. Okay, so we'll ask you. Anyway, just forget about it. Actually don't confuse you. So like, just forget that. So what we said is, here we said this x is actually the distance, critical distance. This cr means this is the critical distance. So it is the same formula. If you see, um, if I write it like this Reynolds number, okay, let's say this is the critical Reynolds number, so it will be equal to the velocity distance, this critical distance, over, it will be the kinematic viscosity. So this is the same thing, we just simplified it. um, for this critical distance, I said xcr equal this gamma Reynolds number over b. We substitute all values, we already know everything. So this critical Reynolds number is given 5 and 10 to the power 5, and we got it is 0.195. So at 0.195, at that distance the transition will start and the flow will become turbulent there. So that's actually the solution of this question here. In some cases, we may ask you in the, maybe in the final exam or in the quiz, you have a flat plate like this. Maybe it is 5 meter long. So this is definitely 0 meter. Let's say this is 1 meter. Let's say this is 3 meter, and let's say this is 5 meter. We may ask, what will be the flow regime at x equal 3? It could be on question, you need to answer, you need to calculate the Reynolds number. We can say, okay, what will be the Reynolds number at x equal 5? Okay, so that can be different types of thing. Maybe will your tutor will discuss this during the tutor session. So that's actually the solution of this problem.